Hello, my name is Stephen Bates, and I'm a Technical Director in the CSTO at PMC-Sierra. What I'd like to do today is talk a little about Nonflash technology and some of the great technology we're developing here at PMC-Sierra to help extend the life of Nonflash in order to enable better, cheaper, and faster solid-state drives. The material I'm presenting is based on a presentation that I gave at Flash Memory Summit in August 2013. What we're going to talk about during today's talks is introduce some of the problems, or the vagaries as I like to call them, of NAND flash today. We're going to talk about rate-adaptive, low-density parity check codes and how we can use them to enhance the performance of solid-state drives that take advantage of the NAND flash that is used inside them today. There's some benefits in using this technology that we've developed here at PMC-Sierra. The first of those is that it makes for cheaper drives. The cost per gigabyte for you, the consumer, is less. The other thing that happens with the technology that we've developed is that it allows you to write to your drives for over longer periods of time, ultimately increasing the overall capacity of the drive through its lifetime. And another thing that we've developed here at PMC is the ability to ensure that the latency of the reads off the drive is kept low all the way through the life of the drive, and not just at the beginning. And this is important for applications such as gaming or office-intensive applications where the need to get the data off the drive as quickly as possible is critical. We're also going to talk a little about some of the other aspects that may impact the drive, such as variable random write performance. I'm going to finish with some conclusions and talk a little about some of the other things that we're doing at PMC to help enable solid-state drives in both consumer and enterprise industries today. NAND flash is a very popular solid-state storage medium today. Many of you will have solid-state drives in your home computers or in your laptops, and solid-state is the way that most tablets and mobile phones store their data today. As such, it's very important for us to make sure that solid-state drives are very cheap in order to enable the market, but at the same time deliver reliable performance and also make sure that your data is not lost. At the same time, NAND flash is inherently not that stable of a medium. It has certain physical characteristics that can lead to errors and loss of data. So what's required is a special controller, such as the ones we develop at PMC-Sierra, to ensure that this unreliable medium becomes a reliable interface to you, the user. One of the things that happens during NAND flash is that it gets degraded as we use it. The usage of a flash is measured in terms of program erase cycles. Every time you write new data to the flash, you have to erase and reprogram it. And every time you do that, a slightly destructive effect inside the device causes it to wear out. Over a period of time, the ability of the drive to store your data reliably is diminished. So the problem that you face is you want to continue to use the medium, but it's becoming inherently unstable. A flash controller, such as those developed by PMC-Sierra, helps mitigate that effect and ensures that even though the medium that you're storing the data on is reliable, you're able to get it back. One of the mechanisms we would use to do this is error correction, or error correction control. In addition to this, NAND flash is not all the same. Different vendors have different types of flash, and even within the same vendor, they process flash at what we call different geometries. And even within that, it's possible to get two flash which are on the outside the same. They have the same part number, but internally they are very different in terms of their behavior. So we have to accommodate the fact that we would like to use flash from different vendors at different times during the life of that flash, and also that within the flash itself there can be variability. As such, we are required to manage the device and also to understand it in advance, because by understanding the medium, we are able to mitigate these effects and ensure that you, the user, gets reliable performance throughout the life of your device. The graph that I'm showing you here is an interesting experiment that we conducted at PMC on one manufacturer's flash. This graph plots the program erase cycles, which, as I mentioned before, is the wearing out of the flash, and the error rate on the flash on the y-axis. As you can see, the error rate on the flash increases through the life. At the beginning of life, the ECC requirements are minimal. However, as the drive is used, the ECC requirements become particularly onerous, especially towards the end of the life. So the bit error rate of a page increases with program erase cycle, which means that using the same error correction technology at the beginning of life as you do at the end of life is very inefficient. In this graph, what we've done is taken the graph from the previous slide and plotted that in green. And I've added two new curves. One of them is for the bad pages on the same flash, and that's the red line. The blue line is the best pages on the same flash. And note that this flash is from the same vendor, it's from the same die, it's from the same silicon location. But however, it behaves very differently. The error rates vary by as much as an order of 20 times at the end of life, and the variability from the beginning to the end of life is over 2,000. What this means is at the beginning of life, it's very easy to keep your data secure and reliable, but by the end of life, it's very, very challenging. What that means is that we have to use different error correction technologies through the life of the drive. In order for us to deliver a quality solid-state drive to the consumer, we're required to reach a certain number of drive fills per day. That is a metric of measurement, a quality metric of measurement for solid-state drives. So for example, a 10 random fill per day solid-state drive constructed with 28% of over-provisioning needs to achieve about 45,000 program erase cycles. If we refer back to the data from the previous graph, you can see that at end of life, the 90th percentile bit error rate is about 1.8%. At the end of life, the 10th percentile bit error rate is about 1 in 1,000. And at the beginning of life, the 90th percentile is about 5 in 10,000. Using the same error correction scheme for all these cases sacrifices user capacity and increases the cost of the drive. What we want to do is notice when the bit error rate is high, and in that case use a lot of error correction, and also observe when the error rate is low, and in that case use less error correction. Using such a scheme, we can make sure that the error correction and the actual behavior of the flash are aligned and maximize the capacity to the user and the performance of the drive. And that is the technology that we at PMC have developed. Low-density parity check codes are well known in the industry. They are a capacity approaching error correction code that uses soft information that we can glean from the flash in order to ensure that the errors on the flash are removed before they are returned to the user. Low-density parity check codes are very popular because they are what we call capacity approaching codes. They have the ability to correct more errors than most other types of error correction codes known today. Quasi-cyclic low-density parity check codes are a subset of low-density parity check codes and are useful because they can be constructed in a rate-adaptive manner. What I mean by that is that it's possible to, at one stage in the life of the flash, use a low-strength low-density parity check code, and at other times use a high-strength. And by doing so, we can match the error rates of the flash to the power of the error correction engine and maximize the capacity for the user. In this example, I show you two cases on the right-hand side of the graph. In the diagram, you can see that on the left-hand side of the diagram, we have a flash page which can store a certain amount of user data. On the right-hand side, we can see a flash page which has a higher error rate, which can store less user data because it has to devote more of the space on the flash to what we call error correction parity. Error correction parity is information that's laid down that is not associated with the user data, but is there to protect the user data. When error rates are high, we have to put down more parity because we need more of that to recover the user data. And that leaves less space for user data. So by managing cases where we lay down more parity and reserve that only for pages that are the very worst, we can maximize overall user capacity of the flash. In addition to this, packing more code words onto the same flash page allows you to increase user capacity of the drive. So the aim of the game is to maximize the green inside these rectangles and to minimize the red, but at all times to ensure that the user data is safe. If we actually look at the capabilities of these low-density parity check codes in relation to the amount of parity that we add to them, we get a graph something like shown here. On the x-axis, we have the number of LDPC code words per flash page. This is related to the user space. On the y-axis, we have both the code rate in blue and the error correction capability in green. What we can see from this graph is that we can trade user capacity for error correction capability. And this is something that our controllers do in a dynamic fashion, tracking the errors on the good pages and the bad pages, and making sure that there's optimality with regard to user capacity and error correction performance. Another benefit of using rate-adaptive, low-density parity check codes is that we can keep the read latency at a minimum all the way through the life of the drive. Read latency is a very important metric for a solid-state drive. If we can minimize the read latency, we can ensure that experiences for the users are maximized. In the graph on this slide, we plot the latency associated with LDPC coding for different rates of code. In a single rate scheme, what would happen is that the latency observed by the user would increase as the drive aged. So your gaming experience on an older SSD would be worse than it would on a new SSD, which would force you to go and buy a new solid-state drive much more often in order to maximize or maintain a maximal user experience. With the rate-adaptive scheme developed at PMC-Sierra, we can ensure that the read latency is kept low by performing a concept of gear shifting and ensuring that the read latency, which is shown in the black line in the graph, is kept to a minimum even as the drive ages. As such, you can keep your SSD for longer and still enjoy that low latency read all the way through the life of the drive. One of the phenomena that occurs when you use a rate-adaptive error correction scheme, such as the one that I've been talking about, is that as your drive ages and we add more error correction parity, we observe that the over-provisioning of the drive diminishes slightly over time. What this means is that the random write performance will drop slightly during the life of the drive. We can manage this using some special techniques inside our controllers to ensure that the consistency of the write performance as seen by the user is maintained. This is important because in several applications, especially those related to database management, we would like to see that the random write performance of the drive, as observed by the host, is kept constant through the life of the drive. What I show in the graphs on this slide is the evolution of the random write performance through the life of the drive. So in the graph on the left, we see that the capacity of the drive is diminished slightly as we apply more error correction parity to ensure that the NAND flash remains reliable as it ages. Consequently, the write amplification of the drive increases and the over-provisioning decreases. However, through proprietary techniques, we can manage this and ensure that at the host level, the performance is constant through the life of the drive. So I'd like to conclude by saying that in NAND flash today, we can see a very different behavior at the beginning of life than we do at the end of life. And applying a consistent or common error correction scheme across all different manufacturers of flash at all points during the life of a solid-state drive is very inefficient and does not maximize user experience and does not minimize cost per gigabyte. PMC-Sierra's error correction technology, which is rate adaptive, is able to match the error correction parity to the behavior of the flash at that point in its life. As such, we maximize the user experience and minimize cost per gigabyte. This technology is based on rate-adaptive, low-density parity check codes. Low-density parity check codes are well understood as being one of the best families of error correction codes known today. By employing these techniques, PMC's controller family can deliver some of the best SSDs on the market today and can ensure that those are delivered at a price that is very competitive and delivers a very good user experience. So thanks very much for watching. If you'd like to find out more, come visit us at www.pmcs.com.